I said at the end of yesterday that since I hadn't left any time to ask questions, we would start an opportunity for you to ask questions right now, if there are any. But you get our opportunities later on. This is what you put them all right now. Let me just very briefly say where we are. We had this program of 7 points, of which we did the first 3. I don't want to go over it, but just very briefly. So we started extremely conservatively with a model theory for language and personal logic. We threw in a very created P. The semantics was modified by allowing this P a tripartite extension, so to speak, consisting of the extension, the anti-extension, and a truth value gap in between. Then that gives us a partial truth definition. The partial truth definition has a logic. It's known, it's strong linear logic. Then we extended these partial models to so-called super models by combining them with complete classical models in which all the borderline cases of P in the base model have been resolved. And we saw that there are a number of things that you can do with these super models you can't do just with the partial model on its own. And some more will come today when we talk about what you can say about the varieties on the basis of these supermodels and the supervaluation theory of which they are ingredients. And then we very briefly discussed the idea that, well, getting from the base model to these complete processifications seems a very rough and extreme idealization. You might think of those complete processifications as a result of successive steps. And so you get what we call a processification structure, where the set of models that is combined with the base model and consists not just, or perhaps not at all, of these complete processifications, but of models that are, like M itself, partial, and the relation of being more partial than or being sharply off is a partial ordering of the set. And there are all sorts of possibilities that gives for logical and semantic analysis that I already announced, and that will come on Thursday. And in particular, it is very tempting, I said, to think of these different sharpenings of M as far as polymer having something to do with different contexts in which they really can be used. So, the next thing then is to see how we might formulate the varieties in a precise way, so that we can then evaluate how good these various stories are that people have given to explain or account for the Sainsbury's paradox. And I take it that, well, first, even if the Sainsbury's is not what defines vagueness, it is a very close companion of vagueness in a lot of cases. And certainly, therefore, as any proposal for the semantics and logic of vagueness should be in a position to say something about the varieties also. So that's indeed one of the things that we should demand of our supervaluation theory, and although I won't talk about it today, also of this modification involving bit by bit specifications. By the way, there was just an argument over a microphone. I think it says been removed in the meantime, or doesn't work. Can everybody hear me? All right. So, what do we want of an account or an explanation of the Sainsbury's paradox? Well, the general view is you should really do two things. A, show what's wrong with the argument. It looks like you apply perfectly valid principles to what look like true premises, and you end up with this radically false conclusion. That's paradoxical, and you want to see how we can get rid of the paradox. One thing is to actually look at the argument carefully, and then use whatever tools we have to show how it's valid. Or alternatively, that's actually what comes out from this supervaluation account, we can show that, contrary to impression, not all the premises of the argument in whichever form we give it can be true. So if they can't be all true, then there's no wonder that together that will lead to false conclusion even if the inference steps are valid. So that's one part, but then also you want to actually give some kind of explanation or understanding of why these arguments somehow look correct. I use the word sound, by the way, in this technical sense. They look sound in the sense that both the inferential means used are valid, are correct, principles of inference, and the premises are true. So it's sound in this technical sense of a valid argument with true premises. Keep that in mind, because you might think in this intuitive sense there's something unsound about these paradoxical arguments, whatever else you want to say about it. So we have to show that it's unsound, either by showing you some of the premises are false, or some of the logical inferences are wrong, and then we want, this is the second task, to explain why the argument looks sound. Okay, repeat myself. So in order to be able to do this for any kind of theory, we first, as I said, must have a formulation of the paradox. And there are basically two forms, and I shall give you three forms, but there are basically two forms in which the argument is typically formulated. What they all have in common is there is one premise that says, call it A0, one particular thing. It's clearly P, it's an unequivocal case of Gregor, an unequivocal case of a bald man. There is another object, we call it A sub n, of which it is clearly false, that it's red or bald or whatever the predicate P means. And then we have a way of getting from this intuitive, plainly true premise to this plainly false conclusion. And so in order to get to the conclusion, we need additional premises to this premise PA0. And intuitively, or Marcus already told us about this writing, and we know what's involved. You can get from A0 PA0 to PAN by a number of successive steps. And these steps involve predications of the form PA1, PA2, PA3, and so forth, where each time the next object, AI plus 1, is so little different from the previous one that in some sense it seems absurd to have called the previous one P and now to deny that of the next one. Now, how can we formalize this? One way is to express this intuition that if P of AI is P, then AI plus 1 is P as well, in terms of a separate conditional. So you get a lot of individual conditionals, as many as there are, so to speak, steps from A0 to A1, from A1 to A2, etc., to get from A0 to AN. So if PAN is the last premise, we get n such conditionals. And let me just show you what the argument looks like, and then go back. So this is one way of formulating it. We've got these n plus 1 premises here, the P0, and then these n premises here, and the other way, or ways of formulating the Sorites paradox, also seen very often, bundle, so to speak, all these conditionals into a single premise. And intuitively, what you want to do is sort of quantify over the arguments. Now, you have to be a little careful there. Let me go back to explain what I mean. In fact, there is a certain danger in some of the literature to really sweep something under the rug that really is a little problematic. So, here is one thing you might want to write down for all n of P of A of n and P of A n plus 1. Sorry. But that's not a formula of our logic, right? I can't quantify over these indices, the A1, A0, A1, etc., AN plus 1, they are distinct constants of my language. There's no quantifying over them. What we want here is a variable. And for all x, if P of x, then something. Now what you often find is P of x prime. What's the prime? Sorry?
The successor.
Exactly, it's something like the successor, it's a function. It's not that x prime is a different variable and you sort of understand it. It's referring to things very close to whatever is referred to by x. That it really is important that you realize that in order to get this two-premise version, you have to actually adopt some kind of function. Here, to make it absolutely explicit, I use a real sort of functor symbol, f, a functor which, in the models that we're interested in, maps each object to one that is very close to it as far as P is concerned. Mark already told about the tolerance principle. This principle, whether it's true or not is not a matter, that if, say, D and D prime are within this tolerance margin with regard to P, then if D is P, D prime must be P as well. So we want a function that does that. And oh yeah, terminology, I will say in a case that I was just describing that these objects D and D prime are within the tolerance margin of P. That means that they're so close that there's no difference between them that can be relevant to the question whether something satisfies P or not. And so this function then must be assumed to have this property that it maps objects onto objects that such that the two are within the tolerance margin. And yeah, the form of the argument now must be, that's what this big N does that we are talking about all the time, that the conclusion of the argument is something you get by repeated application of this F. In these four smart cases, that function is go to the next thing, the next thing, the next thing. It gets more and more and so. And so one thing is to simply wait. I have listed somewhere. All the versions. Yeah. One thing is to simply write down the relevant property of f. Well, you see here, I don't actually talk about the tolerance, or that X and Fx are always the tolerance margin of F, but I sort of take that for granted, and on the strength of that, I then can formalize this conjunction of these conditionals as for all X, if X is P, then F of X is P also. So this is a premise that's justified by the fact that the Fx's are always close to the X's, and the conclusion looks like that. We can also make what I was just saying fully explicit by saying we have, on the one hand, the tolerance principle. This here means that X and Y are within the tolerance margin of P. So this actually is the tolerance principle itself. If they are that close to each other, then if the one is P, the other one must be P also. And then, in addition, we say that the functor F actually always maps things onto things that are within the tolerance margin. And again, we have to still formulate the conclusion as P of what I can reach from A0 through this large number of applications of F. So these two versions are quite close to each other, but the difference is that, yeah, here you have the feeling if anything is the culprit in the argument, it is actually a tolerance principle. Here it's a second premise as a given. But here we've got two extra premises. Now the natural way to think of the analysis is that we are in a situation where A0, F and A0, and F just have the properties recorded here. Well, that is, independently we know that that's true, we know that that's false, and we know that that's true. So the models we're going to look at will be models that verify these two premises, this one and that one, and falsify that, and then you might expect that something funny happens with the tolerance principle. Here it's going to be this premise that's at issue. So these are the formalizations that we will use now, and you should keep them in mind because we'll come back to them. And so now the question is, what can we say about these arguments in the light of the supervaluation theory? So we start with the first version, this one with the n conditionals as premises. And the story, again, as I said, the story has to come in two parts each time. You have to say what's really the matter with the argument from a core point of view, and then you have to say something about why, in spite of what you've just said, the argument nevertheless has this seductive look of being perfectly all right and being therefore paradoxical because the premises are all right and the conclusion is. So the central observation is that if you take any supermodel, base model and a set of complete precision negations, in which this is true, A0 is definitely P, and I assume that that's actually true with the base model M, and similarly for that one, here we've just these constants, right? And, in such a supermodel, if you take any of these complete precisifications, they are complete. They're classical models, right? So they have to actually put each of these objects, A1, A2, A3, etc., either into the positive or into the negative extension. So whatever way they do it, there must come a first point where they put an object into a negative extension. Because eventually that one, we know, is a negative extension. And we start with objects at a positive extension. Now, the good models, of course, will sort of proceed linearly as in the so examples of the Sainsbury's paradox going from red step by step to orange and so forth. But we don't even have to assume that. It's clear that if you have an n, there must be a first element in this sequence that is assigned to the negative extension, not to the positive extension of P. And that means that if n plus 1 is that first element, that the conditional, if A of n is P, then A of n plus 1 is P. That conditional must be false in that chosen n. And that's going to be true no matter which n you pick. So in fact, if you take the conjunction of all these conditional premises in any such supermodel, the conjunction or the whole set, the conjunction is going to be false in any of those n's, or if you like, the set of premises is not going to be simultaneously satisfied in any of those n's. So even if the means by which we get from the premises to conclusion are logically perfectly okay, it's nothing very surprising because the premises cannot just be simultaneously true in all the cases where they're interested in where this paradoxical effect arises. So that's just the first part of the story for this particular book. What do we want to say about the second aspect? Why does this nevertheless look so plausible? And here I'm reporting on a suggestion that was actually made at the time by Richmond Thompson as to how you might use these super models if you actually assume that they have an additional component to the ones we've so far described. This is actually something that was discussed in this paper of mine, 75, 2 theories about adjectives. One of the concerns of that paper, as an issue at the time, was to criticize fuzzy logic. Fuzzy logic is still there and it's extremely useful in electrical engineering from what I understand, but then it's a logic, that's the word, which is based on the idea that sentences are not simply true or false, or maybe true or false or undefined, but that they actually have degrees of truth. And in most of the setups, you just have an infinite truth value space from 0 to 1. 1 is truly true, 0 is truly false, and then there are all these values in between. And one of the problems with these systems is they try then to use these intermediate truth values that sentences can have, or formulas, to define in ways that are reminiscent of what we do traditionally in logic, the logical operators. So, in particular, you want to say the degree of truth of A and B is such and such, given that the degrees of A and B are such and such. You want the conjunction now should be a function from degrees of truth of the conjuncts to degrees of truth of the conjunction, therefore. You can't really do that. And, well, the reason is actually very simple. Well, I can't do it, I mean, people do it and I write it down. But, so one principle that's actually fairly uncontroversial in these logics is that if you form the negation of a formula, its truth value is going to be just the complement of the degree of the value of the formula itself. So these values are all between 0 and 1. So if A has the value say 0.3, then not A will have the value of 0.7. If A is the value of 0.9, then not A will have the value of 0.1 and so forth. Subtract degree of A. Now, if you take a formula that's exactly in the middle, as degree 0.5, then by this principle, negation also have 0.5. Now compare what you get when you form the conjunction of A and itself, and when you form the conjunction of A and its negation. What do we get in the first case if A has the value 1/2? We get 1/2 and 1/2. What should that be in this case? I mean, A and A is just repeating A. It should be the same value that you start out, right? Ought to be 1/2 again, intuitively. What do you get when you form the conjunction A and not A? Both 1/2. Should that be 1/2? So the problem is quite obvious. I mean, it has to do, it's an interesting fact. As soon as you allow for these intermediate truth values, then there's a problem with these binary operators, and that they, if you just talk about the degree, there's input to the degree of the, in this case, the conjunction. You just don't have enough information. You lose information about the structure of the conjuncts. There's an interaction between those intuitively. A and A is not the same thing. Not A, which, for interesting reasons, doesn't matter if you only have the truth value 0 and 1. It has to do with the fact that that's the very simple Boolean algebra, and these operators really do function like parts of a Boolean structure, and you get this tension with the linear order. Okay, so that's the criticism, and in connection with that criticism, the proposal was, well, if we have these supermodels, we can do something that goes a little bit in the direction that the fuzzy logicians want. Because we can assume that we have for our, this is what happened before, no. I mean, it only just went off, did it?
Yeah.
Mm-hmm. It really goes, well, it doesn't, it is not allowed to go to sleep that quickly. It is very much like this morning, but it's... It's just jealous. It doesn't like you to think about it. Well, I've got it printed out, so we can resort to... Oh, no. Ah! What did you
Disconnect and reconnect.
do? Okay.
I have no explanation.
We don't want any explanation of what's going to do. Okay, so the substitute, so to speak, was you've got this, for each of these supermodels, you've got this set of complete specifications. And you can think of something like how true a sentence is in terms of in how many of these specifications it comes out true. So if you can think in some coherent way about sizes of subsets of this set of complete specifications, then that might actually give you a way of talking about degrees of truth between 0 and 1. And you need not be in the same difficulty that I was just talking about. And the reason is that if you have, say, here your entire space N, oh, you don't have to do it. Oh, I see. So these are the complete specifications where A is true, these are the complete specifications where specification B is true. The conjunction of A and B is going to be true in this intersection set. And when we now talk, if you have a probability function on these sets, so yes, the whole set n onto 1, and the empty set onto 0, and this, well, probably something like, I don't know, 1/4 in this case. If I do it right, and there's something like that, maybe 1/3. And now, when we talk about the value of the conjunction, we're not talking about something that we can compute from those values. It has got to do exactly what the overlap is. So we got something or other. It might be 0 if B was not A, then there would be no overlap at all. It can be the same as A and B. A, that can be anything in between. Okay, so that's the basic idea. And then Thomas said, well, you can actually use this to explain in a way why we think of this argument as pretty good, and then puzzled why we get to this prediction. And the idea is take any of these conditionals, PIN, arrow, PIN plus 1. What are the ends in which it comes out false? There are some, those are the ones that make the cut between AN and AN plus 1, as we saw. But there are all sorts of different places where you can make the cuts. So, as against those, maybe it's only one, but in general, those specifications where the conditional PAN arrow PAN plus 1 comes out false, there will be many, many, many others in which it comes out true. So if this probability function that we're talking about reflects this idea in the right way, then these sets, this is the set of those complete specifications in which the cut is made between AN and AN plus 1. That's intuitively a fairly small set. Its complement, and I subtract that from N, is a very big set in comparison, intuitively speaking. That's the set of all the specifications in which the condition PAN arrow PAN plus 1 comes out true. We can explicate in a sense with a probability function that reflects these intuitions that the degree of that conditional, which corresponds to this set, is very big as compared to the degree of the negation. This basically is the set of models, right, where PAN, it's the case that PAN and not PAN plus 1. Okay, so that's the story as far as it goes for this first version. What about the other stories? Let me see. Let's start. Oh yeah, there's one thing that I briefly should also mention, and that is you may still feel that there is something not, well, certainly it's more to say about these cases, but we have been reasoning entirely semantically so far. And there's also this thing about the actual operations, the logical operations you might use to go for the premises of the conclusion. And in fact, in this argument, this first version, and there's only one logical operation that applies, modus ponens. You do it again and again and again and again, and eventually you get to the conclusion. So what about modus ponens? And if these premises are all really entirely true, at least very close to true, how can you get to this plainly false conclusion? And of course, here we have a different perspective. Here we have to say, well, if we think of logical operations as operating at all on sentences which have intermediate, may have intermediate values, then we have to rethink about what they do, and in particular that's true of modus ponens. So the problem here, and it's intuitively clear, is that when you apply modus ponens to a premise A or B, and the premise A, then if A or B and A both have very high values, well, the application will still be a fairly high value, but may actually be lower than the values of both A and A or B. So each time you apply modus ponens, you get a little farther down the slide with the falsity, and eventually you get to this conclusion. So it's a different way of looking, basically the same phenomenon. It's, you have all these different almost true conditional premises, but they're not quite true for different reasons, and it's that combination that eventually leads to this effect. So, I only mentioned this, because that really is a different kind of analysis, right? It's really, we now focus on a particular logical operation that's no longer correct in this setting, rather than arguing the logic is perfectly all right, but if you look at the semantics the way we did, then the premise just can't be true at the same time. So, I'm going to make this brief because otherwise we won't have time for stuff that's to come. Perhaps I'll, I've asked the organizers to put this stuff on the website, so we'll get to that. So what about the second argument? That's the one that has this premise for all x, if P of x, then P of fx. Well, what can we say about this universally quantified conditional in the kind of models we want? Now we want models where already in the base model P of A0 is true and P of AN, actually not, no, P of A0 is false. And then what are we going to say about this formula? Take again any of the complete specifications. Now, in order for this to be true at that specification, all these conditionals we were talking about before, P of n plus 1, P of n plus 1, P of n plus 2, all the instances of this universally quantified conditional have to be true. There's always, as we saw, going to be one, at least, that's not going to be true, and because there is one counterexample, one false instance, the conditional, the universalized conditional is going to be false again. So here, we've got actually a sort of very simple situation. In each of these complete specifications, this is going to be false, and so it's super false, and the conclusion is the same. Right, no wonder then that we can actually get to another conclusion, also conclusion that's also super false. And what do we say about the impression of this actually being all right? Well, I don't know how much we can say about it, but it's basically, I suppose, if anybody could be subject to this optical illusion or illusion, logical illusion, it's confusing the near truths of the instance with the near truths of the universal quantification. The instances can all be near true, really true, and yet if you put them all together, it's the same story. You get something that's falls across the board of the complete specification. So, and then there is, of course, still that last argument with the tolerance principle. I think I'm not going to go into it, but it should be clear. Now, actually, in the models we want, it's the tolerance principle that's going to be false, or very much a separate reason. So I'll leave that for you to ponder over and look at the notes if you want. So next point. Yeah, so there's a little bit in the notes about how good an explanation this actually is, for any of these forms. And that actually is a really important question, technically as well as conceptually. That's what the next two lectures will be about, certainly the one on Thursday. And so I think I'll just not say anything more about that. The next thing that really is important to us at least discuss a little bit, because it's also part of the sort of standard tools in this area, is determinateness, or determinacy. Terms vary. The situation that we have at this point is sort of, yeah, because it's the right word, but there is a certain tension between the semantics we've offered, which allows for these truth value gaps. So there's this tripartite extension stuff. But there is nothing in the object language that you can actually use to express that. So you may actually want something in the object language that, so to speak, makes this aspect of its semantics explicit. Now, what you cannot do is what you might think of doing perhaps at first. And that is the reason as follows. So, okay, I want to express, say, that A is in the truth value gap. Now, what does that mean? It means it's not in the positive extension. And is also not in the negative extension. It is neither P of A nor not P of A are really true. So can't I just say that? Form the formula, you've got it, not P of A, not P of A. No, can't. I mean, and the reason is that that's the wrong negation. We would like this to say it's not the case that PA is true, and we would like this to say it's not the case that not PA is true, but that's not what this negation does. This is actually a plain contradiction. And that's got to do with the fact that how we have to find the not. I mean, the inner negation is precisely what we want here, but it's the same symbol. So we would need, if we wanted to implement this idea, another notion of negation than the one we've got already. And this is something that people occasionally do. You introduce a weak negation so that for an arbitrary formula A, right this way, this is going to be false when A is true, and it's going to be true both when A is false and when A is undefined. That's one way of doing it. But it's actually something that comes with a very high price. And it's something I mentioned very briefly yesterday. It's something that I find very hard to argue for in any philosophical, conceptual way. But it's just a technical fact. Almost all these formal results in this area rely on the fact that the truth definition is monotonic. That is, I already mentioned this, we've got two models, and this one is a sharpening of that one, and everything that's true here will be true there, and everything that's false here will be false there. The only difference is that some of the things that are undefined here get truth value. That was true for the model theory we've given so far. If we throw in this particular negation, as I say it defined, we destroy that. And the reason is obvious. If, say, PA is undefined here, so what is the problem? Then not PA will be true here, and PA can be, A can be in the positive extension, of P and its sharpening. So we get this here, and you get that there. So here this is undefined, and this is true, and in this model that is going to be true, and that is going to be false. So this one goes from true to false in this extension. You don't want that. Now, there's another way, and it actually has some further benefits of formulating. Enriching the object language, which means that allows it to say that something is in truth value gap of P, and that is by using an operator delta for its determinant. And then, intuitively again, P's determinant is definitely true and not if it's not definitely true. And then you can write down something like in 10. Now, from what I've said, it sounds like we've got exactly the same problem with the delta that we had with the tilde. But there is actually a sort of clever halfway house here, which is quite often used, and that is by defining this delta. And it's something that for this weak negation doesn't intuitively make much sense. To define it in these supermodels as simply talking about truth in the base model. So in the base model itself, as well as in all the complete specifications, delta A is going to be true if and only if A is true in the base model. That is a way of preserving this property of homogeneity. And for the supermodels, that's actually quite all right. You get those, occasionally something odd. You get some of these supermodels where PA is true, and definitely PA is false, but maybe that's not all that bad. But when we move from these supermodels to these specification structures, where the intermediate models, so these extensions of P themselves will be partial models, there we might actually want a delta that can speak locally about the truth value at the end. And when we do that, then we're again in trouble. So this is a weak version, and the question, we might come back to it, I'm not quite sure whether we have time, is what happens when we make this definition, this notion delta different from what it's now. Now that is basically what I want to say about delta. Mark, have you got an idea when you want to start? 6. Right. Let me then just talk for 5 more minutes. Then we can have questions if you want them. And if you don't have any questions, you're a fool. So, one question that sort of comes more clearly into focus when we introduce this delta operator, and it's been there all along, and it is one of the deep and difficult conceptual questions about any of the formal treatments of Vagueness that I'm familiar with. It has to do with high order values. So, this tripartite division that we allow for these vague treatments is really tripartite in the precise and the exact in these models, divisions between the positive extension, the truth value gap, and between the truth value gap and the negative extension. You might say that's really not right. I mean, how could there be a sharp division between the cases that are clearly P and the cases that are, the right way to put it, what that to do with, that are clearly borderline? So you might say, well, actually there ought to be, if you model these phenomena in a more sensitive, more sophisticated way, also a kind of fuzzy area between the positive extension and the first instance truth value gap. And similarly on the other side between the first order truth value, we have the negative extension. And now that we've got the delta, of course, there is in a sense, we have incorporated this sharpness of the division between positive extension and truth and legality side. We have, in a way, incorporated it into the object language in virtue of the fact that statements of the form delta A are always bivalent. Delta A means A is true in the base model. If that's so, then delta A is true, and if it's not so, for whatever reason, then delta A is false. And so the delta actually is a sort of signal that there might be something too rough, too simple with the models that we have so far been talking about. In this famous paper of Kate Fine from '75, he actually discusses this problem at considerable length, and he has a very neat construction. Some of it is very complicated, but there's one very neat semantic construction to account for the fact that borderline areas will themselves have fuzzy borders, and those borders will not be separated from the borderline area by a sharp cut, but there will be a sort of a third order area, of borderline, and so on. You can actually sort of set things up in such a way that it comes out formally quite nice. But there is, apart from the fact that we can do this formally, a real question as to whether we should or should do it in this particular way. And it has to do with the fact that when you actually ask yourself, what positive reasons do we have for wanting to have this blurry area between the definite cases of B and the truly borderline cases? What kind of evidence can there be? The intuitive justification for first order borderline cases is, well, there are these situations, bald, you're asked, is this man bald, and you don't know what to say, and you feel it's got nothing to do with factual information. You know exactly how many as you see, how they're distributed, and so forth. You don't think it's got anything to do with your lack of understanding of the semantics, the meaning of the word bald. It's just that, given the man, and given how we use the word bald, we have no guidance as to how to decide the question. When you try to think about what sort of positive evidence there should be for second order, you can't decide whether it's a real case or a borderline case of P. You have to think very hard of what kind of manifestations on the part, say, of speakers could be evidence of that. I'll leave that question up to these, but I think Mark may want to say something about it also. So that's actually was one bit about semantics that I may cut now, and I will come perhaps back to later on the last point. But so this is the end of what I wanted to say today, and questions.
How do people handle defining the semantics of F when there's no clear linear ordering of the domain?
The function of F.
Yeah. There's no clear sense to say the next F.
Well, I'm not sure that this is going to be an answer to your question. I was actually only using the F for the situations where we feel that there is a Soritic situation.
I was just thinking,
Yeah,
you
well,
get
so,
a variety situation, the continuous color.
we have all these color chips, all these days, people that live imperceptibly less tall. And then we can just say we have a function that maps one to the next one. But in fact, do we really have to permit ourselves, as long as we just assume that f maps anything to something else that is in the tolerance margin, which I would choose the argument of the value in the tolerance margin. And so there are presumably such functions. If we've got a function about which we can assert that, that's the third premise of the third argument I gave, then that in combination with this tolerance principle, it doesn't mention f at all. And the first premise, that's actually then what basically allows you to infer the conclusion. Because you first instantiate the tolerance principle to A0 and FA0. A0 and FA0 standard the tolerance relation. So according to the principle, if P of A0, then P of F of A0, and then you apply what is supposed, you get P of F of A0. Then you instantiate again, now with F of A0 and F squared of A0. Again, and so on. So formulating the argument actually doesn't really commit you too much to exactly how this F is to be applied. You just assume you've got an F that has this property, not that you away from the argument. Is that? Yeah?
This is a slightly different take on the color problem, for example. But if you have a range of colors and you have, say, it covers 4 or 5 different colors in the spectrum, there's clearly a notion of sort of being in the middle of a color and being on the edges of the color. Is there a way of dealing with the issue of sort of a canonical red, a canonical orange, a canonical blue, and so on and so forth in this framework?
Well, not really as I've given it, but you might want to say canonical red and the canonical yellow and so forth. They are cases of being clearly in the positive extension of the predicate in question. And so then the models that do justice to this, if we now think of P as representing the color predicate, will have those cases in the positive extension of the base model. There's not an explanation, I mean, it's just sort of reiterating what you're saying is problematic. But I don't know exactly what kind of, yeah.
I'm sorry, I didn't mean to interrupt, but it might be worth adding that in some models, adding another definitely operator makes no difference. So that definitely is just the same as definitely. And that would be true of what Hans was
I
offering.
forgot to say
Whereas
that.
there are more sophisticated models in which definitely is not equivalent to definitely. And then something more like justice to the notion of canonical red could be formalized, because you could decide your number of iterations of the definitely operator and then say, well, that's what canonical red.
Yeah, if one wants to distinguish between canonical red and definitely red, canonical red is even more definite.
Yeah, definitely red.
Right. But in what Hans was presenting, that's just equivalent to definitely red. So one would need to make the models more sophisticated to achieve the effect.
Yeah, I might have said that it's all slide, but so this way, defining definite, if you think of definite as a kind of model operator, it's just as fine. So any kind of iteration that's obliterated.
Changing of the colors?
Yeah.
So I was just going to raise some questions. I don't really have any claims to make, just some questions about supervaluational approaches. So the first thing that strikes one, and Hans has already mentioned this, but perhaps I'll just raise it again, is that on the supervaluational theory, vague predicates typically have three non-empty extensions, so there are two boundaries. The difference between classical model and the supervaluational model is that whereas with respect to a predicate, the classical model offers you a single boundary, in a supervaluational model, with respect to a vague predicate, you get two boundaries. And here's an observation from Williamson on that matter, which I thought we might digest. The idea that our rough and ready use of vague terms does not determine hidden boundaries tells just as much against a pair of hidden second-order boundaries between the true and neither true nor false, or between the latter and the false, as it does against one hidden first-order boundary. So this can be used as a criticism of supervaluational approaches. We could draw a little picture like this of the domain is a kind of slot extending. In the classical picture, the domain constitutes the union of the positive extension and the negative extension. You've got one boundary. And then in the supervaluational picture, you've got two boundaries. So it's quite interesting, I thought a few moments ago when Hans was saying supervaluation gives you these fuzzy things. Well, I mean, that's obviously true in a way. The fuzziness is meant to be in the penumbra. But there's no fuzziness offered about any kind of distinction between positive extension and penumbra, or penumbra and negative extension. So what happens? Well, on a fairly simple-minded approach, maybe this isn't what Fine does, but it was caused to come into my mind by reading Fine's article, not saying what he was actually saying. You iterate. You say, oh, well, if you don't like this sharp boundary between positive extension and penumbra, then just make another division. And at one point I said, you don't make a bad idea better by iterating it. I'm not sure if I still think that, to tell you the truth, but I'm going to address that more on Friday. So this leads to a very general question, which I think is extremely important. It's very important to have a view about it, have something sensible to say. I'm not sure that I'm in that state myself, but anyway. When we're trying to give theoretical account of vagueness, should our theory itself be vague, or should it be precise? So here are some competing considerations. The notion of a precisification or a sharpening in supervaluational theory is either vague or not. And as Hans was using it, it's not vague. Hans now talked a bit about this dilemma, and he thinks it's important. It's no accident that in his way of proceeding, these theoretical notions that we bring to bear in describing language should be precise. And the thought might be, putting it in its simplest way, that if they're not precise, if they are themselves vague, then we've made no proper progress in attaining a theoretical understanding of vagueness. To understand vagueness means understanding it in other terms, not just reusing the problematic phenomenon to redescribe what was problematic. So let me go through the dilemma on either side of this issue now. So supposing then that precisification is a vague notion, then certain problems arise. In that case, how does one know what the right logic is? Let's say the right logic for the meta-language, for the theory that we're trying to offer. Because one of the things that we start out not knowing when we're discussing the nature of vagueness is what the right logic for vagueness is. And particularly in the 70s, that was really the central question. That was the question that Fine was asking, and Hans himself. And you think of the title of Fine's paper, Vagueness, Truth and Logic, the logical inferences, or the impact that vagueness has on logical inference was really a central phenomenon, a central issue for people. So if you allow that the notion of sharpening is vague, then you put the logic of your theory, the tools that you're bringing to bear in understanding, break in your hands. You're now in the dark, as much in the dark about how to proceed in your own theory as you were before, if you felt that a central problem raised by vagueness was how does it affect logic. Second point. Suppose that the notion, we're still supposing that the notion of a precisification or a sharpening is vague, then why should we prefer a supervaluational theory to something more Davidsonian and so-called homophonic? So Davidsonian would think that the right way to give the semantics of a vague expression like red, say, would be as follows. Red applies just to red things. Here, the second occurrence of the word red is an occurrence of it in the meta-language. It's unashamedly vague, the meta-language. And from Davidson's perspective, it has to be vague because one of the targets, according to Davidson, of a semantic theory is to sort of mimic what goes on when an interpreter gets themselves into the position to be able to give an indirect discourse report of an utterance that the interpreter has encountered. So, if I hear the utterance, apples are red, then what a semantic theory has to do for Davidson is to take the utterance as an input and then grind out a theorem which will tell me how to complete the following sentence. The speaker has just said that, and of course, I can complete the sentence perfectly well, indeed perhaps the only completely correct completion is by saying the speaker has just said that apples are red. So from that perspective, you would indeed expect vagueness in the meta-language, that your procedure would be kind of much more direct than the procedure adopted in supervaluation. If the meta-language is vague, then won't we still have Sorites problems? Won't we be able to have arrange precisifications in a Soritical order or a Sorites susceptible order? So those are problems for adopting the first horn of the dilemma. So let's now consider the second horn of the dilemma. Supposing that the notion of a sharpening is not vague, then how is the precise boundary between the three extensions determined? As Hans was saying just at the end, doesn't look as if there's any manifest bit of behavior that will tell us, oh, that's the last red or the last definitely red in the series, and the next thing in the series is borderline. Nothing in our behavior seems to directly correspond to that description. And indeed, one might well feel that nothing could or should correspond to a description of that kind. So can we allow that a smart speak can make the difference between someone who should be placed in the positive extension of child and somebody who should be placed in its penumbra? But, of course, you can arrange children in a Sorites series in which they differ in age by just a heartbeat. And that distinction is going to have to be made on the assumption that the notion of precisification is itself a sharp notion. So I have to say both forms of the dilemma have some pretty unattractive features, but we have to do one or the other. So as I wasn't planning to make a recommendation, I was hoping to elicit some observations. The observations need to be set in the framework of what the aim is of a semantic theory. So I've just mentioned the Davidsonian aim to produce interpretive theorems, as he called them, and those are ones useful to give correct indirect reports to speech. And that definitely requires a vague meta-language. Not that I think Davidson ever recognized this, and it may be indeed unclear how consistent that would be with his emphasis on first-order logic. So that would be one kind of aim of semantic theory. I don't think these aims are inconsistent, but I do think they're different. Another aim might be to attain a theoretical understanding of the semantic and hence cognitive and inferential mechanisms that are at work in the use and understanding of language without simply replicating the phenomenon to be understood. So we have a perfectly good notion of modeling here, and it's no accident that model theory uses the very same word as people use in computer modeling or modeling of the weather. So computer models of the weather don't get you wet, they don't have all the properties of the phenomena to be studied. One can have a theoretical understanding of something which in a way that doesn't just reuse the thing to be understood, but indeed presents what is to be understood in very different terms. So we have to make some decisions on those questions. So that's sort of one question. The next question, how classical is the logic? Well, there's more than one way to define validity supervaluationally. And the most common definition that I've come across in rate is the necessary preservation of supertruth, i.e. global validity as Hans was referring to it. And if you do that, then you do indeed get the often vaunted coincidence between classical validity and supervaluational validity. If you've got no delta, no definitely operator in the object language, and you've got the regular, ordinary kind of supervaluational models, you get the following coincidence within single conclusion conceptions of validity. So you get X classically entails P, and then X supervaluationally entails P. And Shapiro offers that as a theorem on page 68 of his book. The book, incidentally, is on Dropbox. But within multiple conclusion logic, we have a divergence. So in multiple conclusion logic, you define validity as follows. We've got a set gamma of premises, and you say that that validly entails another set, just on condition that if every member of the set in gamma is true, then at least one member of the conclusion set is true. And for reasons I don't fully understand, but which Hans will be able to explain, people who are very serious about logic think that it's very important to be able to characterize logic in the multiple conclusion way. I tell you the truth, I don't really know why that is, but I'm sure there is a good reason. But I just want to point out here that if you adopt multiple conclusion logic, then you don't get a coincidence between the supervaluational and classical logic, because you get that A or B classically entails A, B, treating that as a multiple conclusion, treating A, B as a multiple conclusion. But you don't get that A or B supervaluation entails A, B. And so, for example, A or not A is super true, even if neither A nor not A is super true. So this actually goes back, part of the point here is just to remind one of the way in which supervaluational theories treat disjunction. Disjunction can be true even if neither disjunct is. Whether one wants that or not is a question. And I'm going to give a reason to, anyway, a problem for that feature. When you add the definite operator to the object language, the divide between classical logic and supervaluation logic deepens. There's a nice discussion of this in Williamson's book. I've got an electronic version if anyone needs it. Maybe they left their copy at home. But, have it on the go. Supposing you define, so this isn't actually the definition that Hans gave, but it's more, this is what, and Hans's definition has the advantages he stated just now. But this is a more common way of defining definitely in supervaluational approaches. Definitely A is true if and only if A is true on every precision. If that's the kind of definitely operator you have, then Williamson says, I'm not going to go into the details, that the divergences increase between classical and supervaluational logic. The victims include contraposition, conditional proof or elimination reductio ad absurdum. It's perhaps just worth looking at conditional proof or the deduction theorem just for a moment. Given A, then supervaluationally you can get definitely A. But you don't want as a theorem or as something claiming to be valid, if A, then definitely A. That would make the definitely operator redundant. So you don't get the deduction theorem. Now, we've seen one way, we've looked at one way in which supervaluationism seems to be committed to sharp boundaries. Sort of just makes three boxes: extension to number, negative, positive extension to number, negative extension. And having those three boxes rather than just two is a good thing, in that the inductive premise, the usual inductive premise, for x if x of p, then p holds also x prime, is not super true, and in fact it's super false. So that's good. But then here's something that Hans didn't mention. He came very close to mentioning it, but he didn't. It's not good that the following is super true. There is an x such that x is p, and the next one is not p. That comes out super true in standards or supervaluation models, and in the ones that I think I'm right in saying, and in the ones that Hans was presenting earlier on. So the bad thing, the extensionally quantified thing, the apparent boundary drawing thing, is true on every precipitation or supermodel, since every precipitation draws the line somewhere, though of course there's no one place at which all precipitations draw the line. So it looks as if that second thing, the extensionally quantified formula, is saying that there's a sharp boundary. How else could it be true? It looks as if it must be saying there's someone who is tall next to someone who is not tall, even though they differ in height by less than a millimeter. So I think one of the jobs a supervaluationist has to do is somehow massage this away. One thing they do is say that's not really a correct understanding of the formula. The natural sort of English expression isn't really what's being said. We've really come back to the same problem as the one about all. So supervaluation is, I mentioned, the disjunction is true even if neither disjunct is. And of course, analogously, an existential quantification may be true even if no instance is true, i.e. super true, even if no instance is super true. So as I've mentioned, I think one thing a defender of supervaluations could do is claim that the formula, there is an x such that p of x, there is an x such that p of x and not p of x prime, that the formula is not a formalization of the falsehood that there's the last p in the series immediately followed by the first not p. But then I think one might ask, how in that case would you formalize that particular claim, even if you want to reject it? Let's see the falsehood that you want to reject. I can only say I didn't really get anywhere with that. I'm going to skip this slide. Okay, so this is a bad argument. I'm not going to give you the details. This is a bad argument. So I decided not to. I meant to hide the slide. But this is a better argument. So some people have the following worry about supertruth. Namely, this it doesn't conform to Tarski's schema. So Tarski's schema is that, should be on the board. I don't think it is. Okay, oh, that's because I put it on the previous slide, which is now gone defunct. Okay, so anyway, here it is. Open inverted commas. A, close inverted commas, is true if and only if A. So that's Tarski's schema. So it's called disquotational because it tells you that quoting a sentence and saying of what you've quoted that it's true is equivalent to just the sentence itself. So one can argue, I don't think one can see fairly straightforwardly that if you accept Tarski's schema, you're going to have to accept bivalence. This is something that Williamson argues in in a chapter on supervaluations in this book. So I think you could see it in the following way. Consider the claim that it's not the case that A is true. So not true quotes A. Well, true quotes A is just equivalent to A, so you can replace true quotes A by A itself in the context of not true quotes A. And that just gives you not A. So what you've got is that for A to fail to be true is for it to be the case that not A. So you can see that inconsistent with bivalence. Williamson sets it up slightly differently in his argument. He says that A or not A is supervaluation invalid. So then that gets you, he says, given Tarski, to either A is true or not A is true. So then the supervaluationist is committed to the view that not A is true, that means, of course, super true, if and only if A is false. Right? Super false. And then since A was arbitrary, this means that every sentence is either super true or super false, and in conflict, of course, with the supervaluationist denial of bivalence. So putting it the other way around, if you cling to bivalence, if you hold on to Tarski, you'll hold on to bivalence, and so you won't be able to engage in these supervaluational semantics. Now, why does that matter? Well, Williamson makes a claim, again, I'm not going to defend this, but so these are just questions really I'm throwing out for discussion. Williamson makes a claim that nothing is true unless it satisfies Tarski's schema. You can just tell that it's not a truth predicate if it can't be inserted in the gap quotes A, gap, if and only if A. If you can't put the expression you want to use to express the property of being true, if you can't put it in that gap, then it just doesn't express the property of being true. So that's quite a strong claim. And it does seem to lead, that claim does seem to lead to bivalence. And so that would have a powerful influence on our treatment of vagueness, as it did to Williamson, taken to an epistemic theory. So let me just conclude by listing the questions that I've raised. I'll just shove them on the board, and we've got 5 minutes for discussion. So does supervaluationism do justice to the intuition that vague predicates lack sharp boundaries? It draws just extra boundaries. Should supervaluationist theory itself be couched in a vague or a precise language? Under what conditions and to what extent is classical logic preserved in supervaluation theories? And does the notion of supertruth conform to Tarski's schema, and if not, does this matter? Over to you.
So maybe you'll talk about this tomorrow or Thursday, but so there's a lot of talk about like iterated supervaluationism and like omega supervaluationism, where you iterate it not just like a few times. You can leave all of the meta languages vague, or maybe you have infinite strings of definitely operators, right, in the object language or something like that. Then you would have some sort of you take the union of all the languages, and then you get some sort of limit perspective on vagueness. I mean, so I don't know, it seems kind of a little tricky to me to operate like that, but there are people actually invoking this in defense of supervaluations against claims like boundarylessness, and to accommodate boundarylessness. Maybe could you tell me what you think about that, or tell me if you think it's a plausible way of responding to one?
I think I might pass that question. I mean, it doesn't seem at all plausible to me, but I don't have any serious arguments or even really any serious observations to make, I'm afraid. But Hans, you may have thought about this
one
before.
part of the story, I mean, one part of the answer, I think, one might give is, I mean, the problem of using a vague meta language to do justice to the vagueness of the object language is you want not just a vague meta language, you want a vague meta language, well, meta language with a logic that allows you to prove things about the definitions you get about the object language. That, I think, is something that isn't common between qualitative semantics and truth theory and vagueness. I think that also, I mean, it's all got to do with whether you can derive the passing by conditions in an interesting and revealing way, or a particular way in which the truth definition is set up. So, if you abandon a classical meta language where you think you know what the logic is, for a vague meta language, you better have something in hand there that can do the work that you want the meta language to do. Now, the question is, you can then perhaps try and provide for that by giving a semantics for that meta language in yet another meta language. But of course, in a way, that's just passing the buck. And I don't know how one can actually make real, it's really ignorance on my part, how one might actually make real progress that way, sort of get a grip of at least enough of logic of the meta language that enables you to prove the theorems about the object language you'd like to get by using yet another meta language to give the semantics of the first one, and then, yeah, you need the logic of the second meta language to really show what the logical properties of the first are, and whether going all the way to the limit is really going to help that. It's not clear to me.
Well, but that, so that I think I take the idea to be that at the limit, say at at the union of all the hierarchy of meta languages, you actually do retain some of the properties that you wouldn't have gotten at any stage, any like one of the ordinals, right? So you end up getting, you're able to derive in that language properties of the object language, and in fact all of the other languages in the hierarchy.
I see.
Because that language is particularly, I mean, this is just the idea, I don't think anyone's actually done it, but that it's actually a better quality kind of, it has qualitative properties that are different than the object language.
And if that's really true, I mean, that's really very attractive. Can you give me any reference? Can you give us any reference?
Well, so, I mean, like, Jonathan Schaffer talks about it, Terry Borgen talks about it. It's in their interchanges about whether or not supervaluationism is a plausible theory. I maybe can give you a reference after. But then, I mean, it might be like, kind of in the vein of a Kripke style truth definition, where you get a different, you create a fixed point at the or like omega plus 1 or something, and there's this hierarchy of meta language, and then you have a different property at the limit that you can have it.
You want to come in?
Yeah, actually, just on that point, it would seem that it would be more natural to do it the sort of circular way, to actually have the thing circularly defined, without iterating, because iterative one where